Shall we get started? Those are online. Am I audible?
Yes, sir.
Okay. So, yeah. We completed till potential energy of a spring, right? That was the last concept we saw, and we solved some problems also, right? So, now we have the last topic of this chapter, which is called as collisions, right? So, we'll be discussing the last chapter of this chapter named collisions, right? So, first, even before I explain what collision is, right, I would like to understand what is your perspective of what collision means. So when you hear this word collision, what comes to your mind? Okay, two bodies are going to collide with respect to each other. Can I say this hand is there, this hand is there? Can I say this as collision? Can I say this as collision? Listen to this. Observe what I asked. I'm taking both my hands. There's one object, there's another object. Forget about them being hands. One object, another object. These two objects are touching and moving back. Right? Or this is sitting, this is moving back, or this is sitting, this is moving back. Or both are moving back. This is one type, right? That's what you call it as collision, right? When two objects are going to come in contact with each other and they are going to move away from each other, or they can move together, anything can happen. For example, they can move like this. This is also collision, right? But this object is there, this object is there. The object has come closer, but it has not touched and it has reverted back. Can I call this also as collision? Is what my question is. So that's right. So here, in the first case which I discussed, the objects were coming in contact with each other and they were moving away or they were moving together. Anything could have happened. But in the scenario I explained, the hand was coming closer and it took a turn. Right? See, for those who are online, I'm showing it. I'm saying, I'm asking, the hand is coming closer, but it is just taking a turn. Can I call this as collision is what I've asked, right? And the answer to that is, even that can be called as collision according to physics. Okay. So there is a reason why we are studying this. Because if you observe, the name of the chapter is work, energy, and power. Right. So when I talk about work, what comes to your mind? If there is a force, the force applied on an object is able to cause a displacement in the direction of its application. You say work is said to be done. What is energy? It is the capacity to do work. So whatever work you do is going to get stored in whatever work you do is going to get stored in some form of energy. And what are the forms of energy that we know? Mainly we talk about potential energy and kinetic energy. So one thing is clear, for you to speak about collision, right? Definitely the object has to be in motion. So when I talk about collision, what are the minimum number of objects that are required for me to describe a scenario? Minimum is 2. Maximum can be anything. So for me to talk about collision, I need a minimum of 2 objects. Of those 2 objects, at least one of the objects is supposed to be at least one of the objects is supposed to be in motion for you to talk about this concept, right? So when you talk about collision here, it does not majorly focus on the concept of whether the objects are coming in contact with each other or not, but what is happening to the velocities of the object before a certain instant and after a certain instant, and that instant is what you call it as collision. So the main point that we are going to focus here in terms of collision is all about what is happening to the velocity or what are the changes that are taking place in the object's velocity before and after a point called as or an instant called as collision. Is it clear? So that is where the definition comes from. If you talk about a collision, right? A collision is obviously said to occur between two bodies, either if they physically collide with each other or if the path of one is affected by the force exerted by the other. So an important point to be registered in your mind here is collision does not always mean that the objects are supposed to be in physical contact. If the direction of object is changed, that means that the velocity of the object has also changed in terms of its direction. So if this can happen due to the force exerted by one of the objects on the other, then you can still call that kind of a phenomenon as collision. Okay. And the best example for that is, so here if you see, for a collision to take place, the actual physical contact is not necessary. And the example for which there is no physical contact, but still there is collision existing is the Rutherford's scattering experiment. So what happens? When you study about the different atomic models that were proposed, first you had the Dalton's atomic model, then came the Thomson's atomic model. That was further modified by Rutherford by doing an activity. What was the activity that he performed? Alpha rays. So alpha rays are basically helium-2 plus particles, right? So they are helium-2 plus particles. So what happened when these alpha particles were traveling towards some central core called as nucleus? Till then, there was no concept of nucleus described. So J.J. Thomson's model did not speak about nucleus at all, but Rutherford's model was the first to discover something called as nucleus, which is the central core, which has the positive charge stored in it. Right. So in this case, what happens? You have a positive charge here, you have a positive charge here. Obviously, they both are not going to come in contact with each other. Rather, they will start repelling. So here, which particles are moving? Alpha particles. But which particle is stationary? It is a nucleus. That is why I told you, whenever you talk about collision, you need to have a minimum of two objects. And another important point is at least one of the objects is supposed to be in motion. So what happens is when this helium particle is approaching towards this nucleus, it got scattered in different directions depending on at which point with respect to the nucleus these particles went. You remember? Right? But if you see, there was never a point where the alpha particles came in contact with the nucleus. And this is the best example for you to understand what is collision with respect to physics. Am I clear with this point? Right? So alpha particles get scattered due to which force? We understood that the force is necessary. Here, this force is called as the electrostatic force. So electrostatic force is something that exists between charges. So helium-2 plus is also a charge. Nucleus also has charge. Right? So it happened due to the electrostatic repulsion that was taking place between the alpha particle and the nucleus from a certain distance itself. Right? So we can conclude that the alpha particle has suffered collision with the nucleus. Right? So this is the basic introduction of understanding what collision means according to physics. So I assume that you got some perspective out of it. Right. Now the question is, if we have to talk about the different types of collisions, what are the two major classifications? So the two major classifications of collisions are, one is called as elastic collision. Okay, it's called as elastic collision, and the second is called as the inelastic collision. Okay, now another important point to be asked is, whenever you classify something, right? Whenever you classify something, you're going to have a differentiating factor. You cannot just like that say, these are the two types existing. These are the two types existing on the basis of what? A question mark. Are you able to understand what I'm asking? So, thing is, I told you broadly, collisions are classified into two types. What are they? Elastic and the inelastic. But the question is, on basis of what can you conclude that this type of a collision is going to be elastic or this is going to be inelastic? Unless we have clarity about it, we'll not be able to answer. Tomorrow I'll say, I'll describe a scenario. Okay, I'll describe a scenario and ask you, find out whether this type of a scenario has an elastic collision or an inelastic collision taken place. So what kind of a collision took place, right? So for that, you need some characteristics, right? That is what we are going to see now, right? So first thing is, when you talk about the elastic collision, right? The first thing is the kinetic energy, because what did I say? For collision to take place, what is important? The object should be in motion. Whenever an object is in motion, all the objects that we have or described here have mass associated with them. Accepted? So all the objects we are going to describe is going to have some mass because we are talking about force. So mass is going to be there. And when this object has a speed associated with it, right? So listen. So when an object has a mass and velocity associated with it, what are the two important physical quantities that we can describe? One is linear momentum and the second is kinetic energy. So wherever you see an object having mass and velocity, right? Remember, if both the quantities are non-zero, then the object has both momentum and kinetic energy. Irrespective of whether the question is asking you about momentum or kinetic energy, you should know that fact. Am I clear with that? So I told you on basis of which parameter the collisions are going to get classified as elastic and inelastic. So if you observe, right, in all types of collisions, whether you are going to state whether it is an elastic collision or inelastic collision, the linear momentum of the system is always conserved. So the first important point to be noted here is when you talk about collision, right, whether it is elastic or inelastic, the linear momentum of the system is always conserved. Linear momentum is always conserved. Am I clear with this? But when you talk about kinetic energy, for elastic collision, there will be no loss of kinetic energy. In the sense, kinetic energy is also conserved in addition to the linear momentum. In which collision? In elastic collision. It is not inelastic, in space elastic. So in elastic collision, apart from linear momentum, kinetic energy is also conserved, right? So if that kind of a scenario exists, you can say that the momentum is elastic collision. But in reality, nothing of that sort will be possible. It can only be nearly possible, but you cannot have any kind of a collision where there is no loss in kinetic energy, but it can be close to perfection. Okay, so there is a theoretical concept here. The next point is inelastic collision. So when you talk about inelastic collision itself, we classify it into two other types. One is just inelastic collision, and the second one is called as perfectly inelastic collision. I'll tell you what is the difference between both. Okay, so in the case of inelastic collision, what is already conserved? By default, something is conserved. What is it? Linear momentum is conserved because it's collision. But there is going to be a loss of kinetic energy taking place during collision in the case of inelastic collision or perfectly inelastic collision also. So if you have to say that the collision is elastic, two parameters are to be conserved. What are they? Linear momentum and kinetic energy. Whereas if only linear momentum is conserved and the kinetic energy is not conserved, you call it as inelastic collision. And the same thing will happen. And the same thing will happen in the perfectly inelastic collision also. But the additional parameter here is when you take two objects colliding with each other, after collision, these two objects will start moving as a single object. So if there is a collision, see, there are different kinds of collision that can happen. If objects are colliding, they move apart, right? When the objects are colliding and they move apart, they can either be elastic or inelastic collision, depending on whether the kinetic energy is conserved or not. But if there is a collision that is taking place and after collision, both the objects start moving as a single object. If they stick together and start moving as a single object, you call that kind of a collision as perfectly inelastic collision. Okay, so if two bodies stick together after the collision and they start moving as a single body, when they start moving as a single body, one important point is both the objects will have the same velocity, and that same velocity is what is given a name called as common velocity. Right? So what is going to happen if two bodies stick together after collision and move as a single body with a common velocity, then the collision is said to be perfectly inelastic collision. In such collisions, what is going to happen? Momentum is going to be still conserved, but loss of kinetic energy is going to be maximum. Okay, loss should be there because it is inelastic. The prefix perfectly says that they are sticking together. That's it. Am I clear? So make a note of it. Shall I proceed? Okay, listen. See, this one we will not discuss much. No. The next one is, so I told you basically collision is classified into two types. What are they? Elastic and inelastic. On the basis of what? On the basis of whether there is a loss in kinetic energy or not. If there is no loss in kinetic energy, you call it as elastic. If there is a loss in kinetic energy, you call it as inelastic. Simple. Now, based on the directions or the orientation along which the collision is going to take place, they are again further subclassified as head-on collision or one-dimensional collision. Name itself is suggesting head-on collision or one-dimensional, meaning if, right, if the collision is taking place in such a way that the colliding objects move along the same straight line path before and after the collision. In the sense, let's take this as an example. Let's take the hands as an example. This one line, there's another line. If you draw an imaginary line through this, my hands are moving along the same line. So after collision, if they move along the same line, then you can call this kind of a collision as one-dimensional collision, or more technically, you will call it as head-on collision. So head-on means they are coming in contact along the same line. Why do you call it as one dimension? Because it's a line. The next thing is, you have something called as an oblique or two-dimensional collision, in the sense, if this hand and this hand are colliding along this line, but after collision, this starts moving like this and this starts moving like this. They start moving at a certain angle with respect to the initial line along which they met. So initially they met along one dimension. After that, they are moving along two dimensions. So what is going to happen here is, if two bodies do not move along the same straight line path, if they do not move along the same straight line path, but they lie in the same plane, plane means two dimension, but they lie in the same plane before and after the collision, then the collision is said to be oblique or two dimensional. Oblique means it is making some angle. That is the meaning. Okay. So if I have to represent it diagrammatically, there is an object of mass m1, there is an object of mass m2. They both are moving along the same line with the velocities u1 and u2. Okay, let's say they are undergoing collision. So after collision, what will happen? They will start moving in such a way that this is going to move with the velocity of v1 and this is going to move with the velocity of v2, this m2, meaning if you draw an imaginary line joining these two particles before and after collision, then they will lie along the same line. Are you able to visualize it? So this kind of a collision is what is called as one-dimensional or head-on. And the second is, if the objects are moving along a line, let's say with speed u1 and speed u2, but after collision, right, one object starts moving with velocity v1 like this, and another object starts moving with velocity v2 like this, where this is going to be m1 and this is m2. Now, if I draw an imaginary line between them, this imaginary line is called as the line of impact. If I draw an imaginary line, what is it you're able to observe? Initially, they both are lying along the same line, but finally, what is happening? Each object is making an angle theta1 and theta2 with respect to the line of impact. So this kind of a collision is what is called as two-dimensional collision. But what will happen? These two objects should lie in the same plane. Means you can actually draw a plane through these objects, but you cannot draw a line through these objects. Am I clear with these 2 points? Right? So make a note of this. Let me know once you're done. Okay, listen. Now, we'll see the combination of the types of collision that we discussed. So we are going to see elastic collision in elastic collision in one dimension. Okay, 1 minute. Sorry. So now we'll discuss about elastic collision in one dimension. Right. If you observe the diagram here, there are 3 scenarios that are shown. One is before collision, one is during collision, and the last is after collision. Okay. So before collision, if you observe, the objects are moving along the same direction, where the mass of the first object is m1 and its speed is u1, mass of the second object is m2 and its speed is u2. Okay. Now, during the collision, what has happened? They both are coming in contact with respect to each other. Now, listen to this very carefully. I told you in any type of collision, what is conserved? Linear momentum is conserved. But if we go back to the basics of Newton's law and check, when is linear momentum said to be conserved? That says when the net external force acting on the system is 0. What is it? Net external force acting on the system should be 0 for you to say that the linear momentum is conserved. Right. So if you observe in these cases, right, That is, in the case before collision and after collision, they both are not in contact with each other. So there is no force acting due to one on the other. But during collision, what has happened? They both are coming in contact with respect to each other. Now tell me one thing, there will be a force exerted by M1 on M2 in the rightward direction, accepted? So let me call that force as F1. And there will be a force exerted by M2 on M1 in the leftward direction, accepted? This is called as F2. Now, if these two are considered to be a rigid body, right, what do you think is going to happen? Or what do you think is going to be the relation between F1 and F2? What do you think is going to be the relation between F1 and F2? F1 will be equal to F2. Because since I told that the linear momentum is going to be conserved, the net external force acting on the system before, after, and during collision should be a zero. Right? So according to Newton's third law, what will happen in this scenario is the force exerted by one on the second object is equal to the force exerted by the second object on the first object. This is what happens during collision. That is why if you observe in all the three scenarios, we are saying that the net force acting on the system is zero. That is the reason why linear momentum is conserved. The same thing happens for inelastic collision as well. Are you able to understand? Right? No. So what we need to do in this scenario is very clear that before collision and after collision, the objects are moving along the same line of impact. That is why it is a one-dimensional collision. Okay, accepted. But what is our job is, if the object of mass m1 had an initial velocity of u1 and m2 has a velocity of u2, that is before collision, after colliding, they will again start moving as two separate objects. Now we need to find what are their final velocities in terms of their initial velocities and masses. So mass of the object is not changing because it's not lost. But what is changing? The velocities are changing. So what do we need to do? We need to find the value of v1 and v2 in terms of m1, u1, m2, and u2. So our final expression for v1 and v2 should have only these terms. What are the four terms? m1, m2, u1, and u2. Now tell me one thing. If these two objects are supposed to collide, what should be the relation between u1 and u2? u1 should be greater than u2. Only then this object at the back will be able to go and touch the first object. Sorry, touch the second object. Am I right? So if u1 is greater than u2, this will be able to go and touch this. So when it has touched, this scenario will occur. So after the collision has taken place, they start moving. So what will happen is momentum will get exchanged, but the total momentum will always be a constant. Okay. So after they get exchanged, they get separated and start moving as two different objects. Right. Now, for them to never collide again, what should be the relation between v1 and v2? v1 should be less than v2. Right. So for them to never collide again, v2 should be greater than v1 or v1 should be less than v2. I hope you are able to understand this. So with this scenario, let's start writing the mathematical equations that are needed. First thing, I'm going to write the expression for conservation of linear momentum. What does conservation of linear momentum state? If the external force acting on the system is zero, then the momentum is said to be conserved, in the sense the initial momentum of the system, right? The initial linear momentum of the system should be equal to the final linear momentum of the system. So what is going to be the initial linear momentum of the system? It is m1 into u1 plus m2 into u2. So m1 u1 is the momentum of the first object. m2 u2 is the momentum of the second object. Remember, momentum is a vector quantity. So you should always be clear with your directions. Here, since u1 and u2 both are taken to be in the same direction, I'm taking both of them to be positive. Right? This is the initial linear momentum of the system. What is going to be the final linear momentum? It will be m1 v1 plus m2 v2. Right? So can I write this as m1 into u1 minus v1 is equal to m2 into v2 minus u2 by rearranging the equation? And I'll call this equation as the first equation. Make sense? I just rearranged it. I took m1 to one side, m2 to the other side, and we wrote this. The second thing is, since you're talking about elastic collision, what are the physical quantities? What are the physical quantities conserved? Kinetic energy of the system is conserved. So if I talk about the kinetic energy of the system, what is the initial kinetic energy of the system? Half m1, tell me, half m1 u1 square plus half m2 u2 square is equal to half m1 v1 square plus half m2 v2 square. Right. So what is going to get cancelled here? Half is lost. So half is going to get cancelled. So half m1 u1 square plus half m2 u2 square is equal to half m1 v1 square plus half m2 v2 square. Now again, I will take m1 terms on one side. So I will write m1 into u1 square minus v1 square is equal to m2 into v2 square minus u2 square. Let me call this as equation number 2. Accepted? I did the same kind of rearrangement. Only difference is here you had u1, u2. Here you have u1 square, u2 square. Okay. Now I'm going to start solving these two equations simultaneously. Observe. So I will take the second equation. The second equation says m1 into u1 square minus v1 square is equal to m2 into v2 square minus u2 square. Right? So this is the expression I took. Okay. So what does the first equation tell us? So first equation says m1 into u1 minus v1 is equal to m2 into v2 minus u2. Am I right? Now thing is, this expression, divide this expression with this. Right? The sense, divide this with, or I will write another step. Listen to this. I'll write this as m1 into, observe, u1 minus v1 into u1 plus v1 is equal to m2 into v2 minus u2 into v2 plus u2. Am I clear with this? So basically a square minus b square, we have written it like this. Now divide this equation with this. That is going to be m1 into u1 minus v1 and divide this expression with m2 into v2 minus u2. Right. So what will get cancelled? m1 into u1 minus v1 and m1 into u1 minus v1 is gone. Similarly, m2 into v2 minus u2 and m2 into v2 minus u2 is gone. So you will get u1 plus v1 is equal to v2 plus u2. Rearrange this equation and write it. From this, you can say u1 minus u2 is equal to v2 minus v1. Now we know that whenever you write v2 minus v1, you can call that as relative velocity. Or u1 minus u2 also you can call it as relative velocity. If you observe, this is relative velocity, this is also relative velocity. But what does this speak about? This speaks about the relative velocity of approach. It is called as the relative velocity of approach. And this v2 minus v1 is called as the relative velocity of separation. So are you able to understand 2 points? One is, why do we call it as relative velocity? Because it is the difference in the velocities. But why did we give the name as approach and separation? Because for these objects to approach, I told you one condition. What is it? U1 should be greater than U2. That is why U1 minus U2 is relative velocity of approach. So after they have got collided, they are getting separated. So during the separation process, what is the condition? V2 is greater than V1. So V2 minus V1 is called as the relative velocity of separation. Am I clear with this point? Right. So if I take the ratio of them V2 minus V1 divided by U1 minus U2, this has a name called as, first of all, V2 minus V1 by U1 minus U2. In this case, what are you going to get? You will get it as 1. Am I right? See, if I divide it with U1 minus U2 on both the sides, V2 minus V1 by U1 minus U2 is 1, right? So this ratio, which is given by the definition, relative velocity of separation divided by the relative velocity of approach, is given a name called as coefficient of restitution. So it is called as the coefficient of restitution, and it is represented by the symbol E. So about this term, we will learn in detail later. Okay, I'm just introducing this term, and remember this 1. So in this case, in the case we are discussing, what is it? It is the elastic collision in 1 dimension. So what is the coefficient of restitution value coming out to be? 1. Have that in your mind. So am I clear till this point? Right. But before I started the derivation, I told you one thing. What is it? Our job is to derive the value of V1 and V2 in terms of M1, U1, M2, U2, 4 parameters. So for this, what I will do is I'll take this as the third equation. I'll take this as a third equation. Now, from 3, so if you observe from 3, can I write V1 is equal to V2 plus U2 minus U1? Can I write it like this? V1 is equal to V2 plus U2 minus U1. Let me call this as 4, and I will use the fourth expression, right? I'll use the fourth expression in the first expression. Remember, 4 is here. This is actually second. I wrote it from the previous slide, and this is the first equation. So what I'm going to do is I will take this and substitute it here. That is all I'm going to do. So when I do that, observe, I'm going to have M1 into U1 is U1 only minus, what is the value of V1? It is V2 plus U2 minus U1 is equal to M2 into V2 minus U2. So I need to collect all the V2 terms from here, and all the known terms, I'll push it to the other side and write the expression for V2. If you observe this, it is going to be M1 U1 minus M1 V2 plus M1 U2 minus M1 U1 is equal to M2 V2 minus M2 U2. Okay. So collect all the V2 terms on one side. So since here V2 is having a minus sign, I'll push it to the other side. So when I push it to the other side, M1 U1 plus M1 U1 minus, okay. Yes. So here it is going to be, minus, and this is plus, right? So M1 U1 plus M1 U1 is going to give us 2 times M1 U1. It's going to give us 2 times M1 U1. And this minus M1 U2 is there. M2 U2 will come this side. So it will be plus M2 minus M1 into U2. Check this. So minus M2 will come to the left as plus M2. So plus M2 U2 minus M1 U2. So what is common? U2 is common. I took out. So M2 minus M1 is equal to, now tell me what will happen. Minus M1 V2 will go to the other side, and you have minus M1 V2 and M2 V2. So what is common? V2 is common. So V2 into M1 plus M2. So bring this M1 plus M2 to the left hand side. So you will have V2 is equal to, I'm just writing it in the reverse. V2 is equal to 2 M1 U1, 2 M1 into U1 divided by what is there? M1 plus M2 plus M2 minus M1 plus M2 minus M1 divided by M1 plus M2 into. So this is the final. So this is going to be the final expression for V2, right? This is going to be the final expression for V2 in terms of M1, U1, M2, U2. Am I clear with this? So first make a note of this. This is a very, very big derivation. Those are online, are you able to understand?
Yes, yes, so
Done? Derive this instead of directly writing it. Derive it instead of directly writing the answer. Shall I proceed? Later. Okay. Done? Listen. So if I look at the third expression, then I have u1 plus v1 is equal to v2 plus u2. Right? So this implies v2 is equal to u1 plus v1 minus u2. Am I right? So let me call this as equation number 5, and I will use 5 in 1. Right? So if you recollect, no, first equation is m1 into u1 minus u2 is equal to m2 into v2 minus v1. Okay. So m1 into u1 minus v1, I am leaving it as it is equal to m2 into what is the value of v2? This thing. So u1 plus v1 minus u2, and you already have a is it right? V1 is getting correct. So listen. One minute. There is a mistake. So v2 is equal to u1 plus v1 minus u2. u1 plus v1 minus u2. So m1 into u1 minus u2 is equal to m2 into. Oh, sorry. Wait. So now it is m1 into u1 minus u2. Right? m1 into u1 minus u2 is equal to m2 into v2 minus v1. But is it v2? Why is v1 getting cancelled? It's not get. Sorry. Oh, there is the expression. No, sorry, I wrote wrong. Here I wrote it wrong. Huh? Oh, okay. Yeah. So I'll come from this step. This step is clear, right? Right. So what is the first equation? m1 into u1 minus v1 is equal to m2 is equal to V2 minus U2. Am I right? So we will take the fifth equation and substitute it in the first equation. Then what are we going to get? M1 into U1 minus V1 is left undisturbed. So is equal to M2 into what is going to be the value of V2? It is U1 plus V1 minus U2, and you have a minus U2. So M1 into M2 into U1 plus V1 minus U2 minus U2. So what will this become? This will be M2 into U1 plus V1 minus 2 times U2. So U1 plus V1 minus 2 times U2. So collect, first expand it, then you will have M1 U1 minus M1 V1 is equal to M2 U1 plus M2 V1 minus 2 M2 U2. So collect all the V1 terms on one side and all other known terms on the other side. So take M1 V1 to the other side, take this M2 U1 to the left hand side and M2 U2 also to the left hand side. So what are you going to get? M1 U1 and this M2 U1, when it comes to the left hand side, what will happen to it? It will be M1 minus M2 into U1. Are you able to understand? So M1 U1 minus M2 U1. So M1 minus M2 into U1. So minus 2 M2 U2 comes to the left hand side. It will be plus 2 M2 U2 is equal to, how much are we going to get? M1 V1 plus M2 V1. It is going to be M1 plus M2 into V1. So what will be the value of V1? So V1 will be equal to, it will be M1 minus M2 divided by M1 plus M2 into U1 plus 2 M2 U2 divided by M1 plus M2. And remember, these two expressions of V1 and V2 are to be remembered. Okay, you have to apply it as a formula in the problems. So wherever there is a problem based on elastic collision in one dimension, this is going to be the value of V1 and V2. When you're substituting it in the problem, right, you need to take the proper sign convention of U1 and U2. Okay. So this is all about the derivation. Make a note of it. Right. Are you done copying? Okay. Listen. So I'll tell you how to remember these equations. If you observe, the values are V1 and V2. Okay. So listen to this. First, I'll tell you for V1. Something into U1 plus something into U2. Right? That is a pattern. Now, the denominator is always going to be M1 plus M2. Here also the denominator is going to be M1 plus M2. So here, if you observe when you're writing it for V1, the numerator will be M1 minus M2, and here it will be 2M2. Right? That's what we got. That's what U2, I already wrote it outside, no? Did you understand? So you should write it as M1 minus M2, and there you will write it as 2M2. Here also a similar kind of a pattern is written, something into u1 plus something into u2. The denominator is still going to be m1 plus m2. Here also the denominator is going to be m1 plus m2. But what is going to be the difference? Here when you write 2m2, here it will be 2m1 and here it will be m2 minus m1. So one, if you look at them, right, one of the numerators will be difference. The other one will be 2 times some mass. So for V1, what will happen is the first term will have the difference and the second term will be 2 times mass of the second object. Whereas when you write it for V2, the second term will have the difference and the first term will be 2 times the mass of the first object. But the point you need to remember here is when you write it for V1, it is 1 minus 2, M1 minus M2. When you write it for V2, it is M2 minus M1. Okay. So this is how you can remember. Okay. And as I told you, these two are very, very important formulae. Clear with this? Done. Yeah. You're done. Right. So the next concept that we'll discuss is about perfectly inelastic collision. Right. So I already told you what is inelastic collision. So in the case of an inelastic collision, linear momentum is still going to be conserved, but the kinetic energy is going to be lost. Right. But whereas when you talk about a perfectly inelastic collision, that too it is taking place in one dimension, what should happen? So both bodies should stick together and they should move along the same line of impact before and after collision. So let's take a scenario like this. So there is an object of mass m1 which is moving with the speed u1 and there is another object mass m2 which is at rest. Okay. Now after collision, if they both stick together and start moving as a single object, they're going to have a common velocity v associated with them. Now our job is to find what is the value of that v. Okay. So what will happen is, since in the case of inelastic collision, only linear momentum is conserved, what can I conclude? M1 U1 plus what is the momentum of the second object? It is 0 is equal to, now both the objects are stuck together, right? So what is going to be the combined mass of the system? It is going to be M1 plus M2 and their velocity is going to be V. So the common velocity is going to be equal to m1 u1 the whole divided by m1 plus m2. That's it. So if at all in a problem they ask you to find the common velocity, all that you need to do is apply the conservation of linear momentum. I would rather suggest don't even remember this like a formula. Okay. All you need to do is apply the linear momentum, the conservation of linear momentum with proper directions. In the sense, if you take the rightward direction to be positive, consider the momentum to be positive. Leftward, you take it as negative. Depending on the movement of the objects, apply the linear momentum conservation with proper sign and solve it. Okay. Done? Okay, listen to this. The next concept we'll see is elastic collision in 2 dimensions. Right? So when you talk about the elastic collision in 2 dimension, it is also called as the oblique collision. Right? So what should happen since they use the word elastic here? What is conserved? Linear momentum is conserved and the kinetic energy is conserved. So they both are conserved. Right? So if you have a scenario like this where there is an object of mass m1 moving with a speed u1 and it is colliding with another object of mass m2 which is at rest. Right? So after collision, what is happening? With respect to the line of impact, m1 is moving, making an angle theta 1 with respect to the horizontal, and m2 is moving, making an angle theta 2 with respect to the horizontal. Basically, it is a line of impact, right? So what I'm going to do is I'll frame the equation and show you of how to handle this, right? So in the case of one-dimensional collision, what did we apply? When I applied the conservation of linear momentum, I took m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. But here, the only difference is you need to apply the concept of linear momentum conservation along both the directions in which the object is confined to move. So in the case of one dimension, the object is confined to move only either along x direction or y direction. Here, what is happening? The object is having a combined motion of x and y because the velocity of the object is in such a way that it can be resolved into x component and the y component. So when you apply the conservation of linear momentum, only thing is apply it along each axis individually and then solve it along x direction. So if I take it along x direction, tell me what is the equation I can frame. The initial linear momentum of the system is m1 u1 plus m2 into 0 because it is at rest is equal to. Now tell me one thing. If the velocity of the first object is in this direction, the velocity can be resolved into 2 components. What are the 2 components? V cos theta, sorry, V1 cos theta 1 along the horizontal and V1 sin theta 1 along the vertical. Why is it so? Because if this is theta 1, this is also theta 1. Right? Because they both are parallel lines. So what is going to happen? I will write it as M1 V1 cos theta 1 plus. What should I write? M2 V2 cos theta 2. So let me call this as equation number 1. So this is the expression you're going to get using the conservation of linear momentum along x direction. So if I apply the linear momentum conservation along y direction, what am I going to get? Initially, if you observe, the linear momentum of the system is confined only along x direction. So initial linear momentum along y direction is 0 because u1 is there along x, there is no velocity along y, and m2 by default is at rest. So 0 is equal to, can you tell me what should I write there? For the right hand side, I will write m1 v1 sin theta 1 plus m2 into minus v2 sin theta 2. Because v1 sin theta 1 is upward. If you take upward as positive, v2 sin theta 2 is downwards, it is negative. Right? So when you rearrange this equation, you will get m1 v1 sin theta 1 will be equal to m2 v2 sin theta 2. Okay. This is the expression you will get when you apply the linear conservation momentum. Sorry. When you apply the conservation of linear momentum along y direction. Is the point clear? So after you frame these equations, depending on the number of unknowns you have in the problem, you can start applying the conservation of kinetic energy also. Okay. So that should be chosen by you depending on the number of variables. Clear? This is the word I told you in the beginning, right? So the next topic we are going to see is coefficient of restitution. So coefficient of restitution is going to give us the measure of degree of restitution of collision. And how is it defined as? So it is defined as the ratio of the magnitude of the relative velocity of separation. So it is V2 minus V1 inside a modulus divided by U1 minus U2 inside a modulus, right? And this is what we call it as the coefficient of restitution. Now let me tell this. It is defined as the ratio of the magnitude of the relative velocity of separation after collision to the relative velocity of approach before collision, and it is represented by the symbol E. Okay. So make a note of this definition. Okay. So based on this, when you prepare a table, right? If you talk about the type of collision, so when we talk about elastic collision, right? We prepare a table for type of collision, kinetic energy, coefficient of restitution, and the main domain. Okay. So when I talk about this collision, that is elastic, kinetic energy is conserved. So what is the coefficient of restitution in the case of it? It is 1, right? So where can you observe this taking place? Between atomic particles. So between atomic particles, you can say that it is elastic collision because they are not coming in contact with each other. Okay. Next. What about inelastic collision? So inelastic collision, kinetic energy is not conserved, and the coefficient of restitution is going to be somewhere between 0 and 1. So suppose in a problem, they say that the coefficient of restitution is 0.5. Define the type of collision. What will it be? Inelastic, right? So when it is between 0 to 1, it is going to take place between ordinary objects. So what about the third case? That is a perfectly inelastic collision. So in perfectly inelastic collision also, there is going to be kinetic energy loss, but the loss in kinetic energy is going to be maximum. So it is going to be maximum. And in this case, the coefficient of restitution is taken to be 0 because what happens to the objects after collision? So after collision, they will stick together. So V2 and V1 are the same. They have a common velocity. You know, when V2 is equal to V1, if you substitute it here, E will be 0. So the coefficient of restitution is going to be 0. And this is an example where you can say perfectly inelastic collision takes place during shooting, in the sense when a bullet is entering an object. Let's say there is a wooden plank, there is a bullet that is entering the wooden plank, then what will happen? The plank and the bullet together will start traveling as one object. Unless and until the bullet is going to come out of the other side, let's assume that the bullet is stuck inside the plank itself. Then what is going to happen? The plank and the bullet will start moving as a single object. That is an example of a perfectly inelastic collision. Okay. So when you talk about the super elastic collision, here the kinetic energy is going to increase and the coefficient of restitution will be greater than 1. And it takes place in the case of explosions. Okay. But in all the cases, what is conserved? It's a linear momentum that is conserved. Okay. So with this, the chapter is over. You have textbook? Anyone has textbook? In that, there will be one problem, example problem based on oblique collision. Tell me which page it is. There will be one nearby. There will be one problem based on oblique collision. Example problem. 6th chapter. 6th or 5th chapter. First chapter is deleted, no 5th. Hold other. Just hold. Okay. Is that the new one? Other. Is new order? You don't understand. 6th chapter na padasara. Physical word in the past. Sir, okay. It is still okay. If it is old book, example is 6.13. If it is new book, I'm assuming it is example 5.13. Okay. So that 5.13 is a problem that is based on oblique collision, which you people try. I'm leaving it to you. So example 5.13 from your NCERT. It's an example based on oblique collision, but they have not given you the complete solution. They will say that follow these steps on solving a mudichiruvaanga. That is why I'm asking you to do. You need to apply a little bit of trigonometry. The thing is, when the objects start moving away, they'll start moving at 90 degrees with respect to each other. In the sense, what will happen is, they will start moving perpendicular to each other, means θ1 plus θ2 will be, when they move perpendicular to each other, what is the value of θ1 plus θ2 will be 90. So θ2 will be 90 minus θ1. You can take that and substitute it here and then solve it. Okay, so you'll have sine of 90 minus θ1, which will be cos θ1. So you need to apply that and solve it. I'm leaving that problem to you. Okay. So with this, the chapter is over. Okay. So what is the time? 5:55. Okay. I'll stop with this. So maybe I'll solve few problems, 5 to 6 problems in the next class, post which I'll be starting with the 7th chapter. And as I told you, next Saturday we'll have on which chapter? Newton's laws of motion. So start preparing. Okay. Start working on it. Any other questions? Clear? If you're going to bunk the test in which, for example, punishment will be tougher paper. அதுக்கு இந்த பேப்பர் எழுதிடலாம். You'll at least I'll have a mix of questions where you will have theory and problems. அடுத்த பேப்பர்னா மெயின்ஸ் லெவல் ப்ராப்ளம்ஸ் தான் கொடுப்பேன். அதுதான் பனிஷ்மெண்ட். பண்ணலன்னா 10 வாட்டி எழுத வச்சு. அதுக்கு இதுவே பெட்டர்ல ஒரு வாட்டி எழுதிட்டு போங்க. 1.5 hourல வேலை முடியும். சரியா? Okay, those are online. Am I clear? You are filling
Yes,
the book.
sir.
No? Yeah. So anyways, you are writing the book there, no? Caller. You are writing, no? You are making. So during the entry, make sure you write that. You mentioned it. No? Okay. So we'll wind up with this. Take a break for 10 minutes. What is the time? 6, sir? 6:10 we'll start off the math class. So those who are online, if there are no questions, we can wind up. You can be